I'll begin with a word of prayer. So, Dearly Father, we thank you for this day. I just pray you to use this time to your glory, Lord. Help the students to just, as they prepare for the test, just to think of any questions they need to ask. And I just pray that you be glorified in this time we have here, Lord. In your name I pray. Amen. So, questions? And I'll speak at once. Oh, okay, yes. Oh, third homework, okay. I was like, I mean, I wish we had instantaneous velocity in the first homework, but I feel like I need to ask that algebra homework, otherwise things will go badly in here. Of course, they might still go badly if you guys don't know algebra. We'll find out soon. Sorry, too soon? Oh. So homework number 3, which number? So your question is how to find instantaneous velocity? Oh, okay. That actually is not too bad. So instantaneous velocity. Instantaneous, I can't spell. Velocity. They're fixed. Ha 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 ha. So if you're given s of t, so that's like the position at time t, then the instantaneous velocity we denote v, and it's just equal to ds dt. Or if you like, s prime of t. So for example, if I had s of t equals to 3t squared minus 7t plus 2, and I wanted to find the instantaneous velocity at, say, time t, well, that's easy. I just differentiate. So ds dt, which is the instantaneous velocity, it's instantaneous rate of change of s with respect to t, what would you get here? You'd get power rule. Yeah, 6t minus 7. So this would be, we denote it v of t. It's the velocity at time t. If I wanted to find the instantaneous velocity then at a particular time, you pick the time anytime you like. What? Time 2. Okay, so then v of 2 would be the instantaneous velocity at time 2, and you just plug in 2. So 12 minus 7, otherwise known as 5. And then, of course, in a given word problem, it might have appropriately attached units, feet per second, meters per second, kilometers per fortnight. I mean, whatever system of units floats your boat. But yes, sir. I'm sorry, ma'am. It's my default. What's the acceleration? So this is velocity, right? Velocity. Acceleration, usually that's dv dt. That's the rate, the instantaneous rate of change of velocity with respect to time is the acceleration. Yeah, the second, exactly, the double derivative, the second derivative. So like here, the acceleration at time t, or just a is dv dt. So for this problem, it's just 6. This is a constant acceleration problem.
But wasn't there a problem where it asked the change of, was it change of velocity between 2 times?
Oh, to compare the average acceleration to the instantaneous? Yeah, there might have been a problem like that.
And that's not with the velocity, but you just plug in the difference.
Yeah, now this problem, problem number 3 of homework number 3, it compares the average velocity to the instantaneous velocity. Average velocity, v average, basically you take the change in the position divided by the change in time. So like s of t2 minus s of t1 over t2 minus t1, that gives you the average velocity from time 1 to time 2. The average acceleration from time 1 to time 2 would be something like this. Although I really don't think I'd ask about that, but if I was to, it would be this. I mean, honestly, if you can understand average velocity, you can easily understand average acceleration. So, as to confuse less students, I'm more likely to ask about the average velocity if I'm asking about average. Or just the average rate of change of f with respect to x. Yeah, also known as the slope of the secant line as compared to the tangent line. Tangent line is connected to the instantaneous rate of change, whereas the secant line is connected to average rates of change. I want to agree. I'm not sure what you're referring to.
Can you repeat the question that you would ask that is relative to the secant?
Oh, sure. For example, I could ask something like f of x equals to x cubed plus 3x. Find average rate of change with respect to x over, say, x equals to 1 to x equals to 3, you know, and then compare to, say, the instantaneous rate of change at x equals to 1, right? So the average rate, you'd get the change in y over change in x, which here would be, so I do f of 3 minus f of 1 divided by 3 minus 1. So what's f of 3? 3 cubed?
27, 28.
Yeah, 27 plus 3 times 3, right? 27 plus 9. Yeah, 36. What's f of 1?
4.
4. So I get 36 minus 4 over 2. In other words, 32 over 2. In other words, 16. In contrast, f prime of 1. F prime of 1 is the instantaneous rate of change, right, at 1. And there you just say, so what is f prime? F prime of 1 equals what? Well, I'd calculate f prime of x, which is what? 3x squared plus 3, then plug in x equals to 1, and that gives me what? F prime of 1, 3 times 1 plus 3, so the instantaneous rate of change there is 6, whereas the average rate of change happened to be 16. There's lots of other average rates of change, right? If I picked a different thing other than 3, we'd get different average rates of change, right? But the instantaneous rate of change of x cubed plus 3x is uniquely given as 6 if I'm fixing the point of consideration at 1. Because there's a unique tangent line, and the slope of that tangent line is this instantaneous rate of change of y with respect to x. Yes, sir?
I'm still struggling with the questions with the piecewise functions that say, like, make it so that this is our, like, for instance, specify the values of a and b so that f is continuous and has a derivative at a certain point.
Sure. How about this? Square root of x plus 2, and we'll do ax plus b. And let's make this 0 less than or equal to x less than 1, and x greater than or equal to 1. We want to choose a and b, which make this function continuous and differentiable everywhere.
You meant to make that an x, I think, so that you said 1 is greater.
Yeah, well, that's safe to say. Yeah. Okay. So we need continuity, and first of all, let me just go ahead. I think maybe a better way to organize our work, now that we're more comfortable with differentiation, is just to write down the derivative. What is the derivative function? You differentiate each case separately, all right? So let's see here. F prime of x, we get, oh man, we don't know how to differentiate that.
Now you put it into a half.
It could be the whole thing in the power of a half.
Here, let me make this better. let's say 2 plus the square root of x there. That now it's friendly. We will soon learn how to differentiate the other thing I wrote, but one thing at a time. So f prime of x is 1 over 2 square root of x for 0 less than x less than 1. I guess I can't throw in 0 is troubling. If you look, it's kind of funny. If you look at the square root function, it looks like this, right? So what happens at the end point? What's the slope of the tangent? Right, so the derivative of the square root function actually doesn't exist on the endpoint of its domain. That's why I have to throw out 0. And this thing is a. Right? And so basically the question is what's, here I'm saying for x not equal to 1, this is how to define it. What do you want to make f prime of 1? Well, it should be the limit as x approaches 1 from the left of f of x, right? Should be equal to the limit as x approaches 1 from the right of, f prime of x. I want to make the derivatives match up. So from the left, what's the value of the derivative at 1? I get 1 over 2 times the square root of 1, right?
Yeah.
From that piece. And from the other piece, well, that's easier. It's a. Aha, so that's the value of a. But how do I pick out what the value of b is? So this gives differentiable at x equals to 1 once we make the right choice of b, once we make right choice of b to complete the thought. How do we choose b? Well, we also need continuity of the function at the pasting point.
So it has to equal from the same side, so a would equal b, right?
Well, I don't know. I need the limit. I need the limit as x approaches 1 from the left of f of x to equal to the limit as x approaches 1 from the right of f of x. I need the left and the right limits to match up in order to have continuity there. So so look at the formulas. What do we have? From the left, we're working with 2 plus the square root of x, right? So from the left, I get 2 plus the square root of 1 when I take that limit. From the right, what do I have? Yeah, so that goes to what at 1? Yeah, a plus b, right? So therefore, b is equal to 2 plus the square root, 2 plus the square root of 1. I think I can simplify that, yeah? Square root of 1? 1, yeah, okay. So this is 3. So it's 3 minus a, but remember a was 1 over, 1 half. This is 1 half, right? I've written 1 half in a rather stupid looking way. So this is 3 minus 1 half, which is otherwise known as 6 halves minus 1 half, which is 5 halves. So therefore choose a equals to 1 half and b equals to 5 halves, and that'll do it. So again, just to summarize the idea of this kind of problem, we need to impose continuity and differentiability at the place where we glue the two pieces together.
Okay, so you have to find the derivative of both first, and then you use that to make the derivatives equal to each other, basically?
Yes, yeah, find the derivative on each piece and make them match up.
Okay.
Yeah. Where did I get the... Oh, this is 3. If you'll allow me this manga style calculation. 3. So I solve for b. Yeah, me too. I mean, look, over here I should have written a is equal to 1 half, but I'm not thinking very clearly right now. So for some reason, 1 over the square root of 2, the square root of 1 was like, I don't know how to simplify that. Sorry. I've used all my mental facilities to create this calculus 3 test I'm giving in the next period. Don't worry, I've gotten that out of my system with them, so your test will be easy. Yeah.
For that part above the can you plug in 1 to get the variable that
plug in, yeah, that's what I'm doing, is I'm plugging one into the left piece and to the right piece to take the limits.
Does it say for x, can't
Oh, because it's at the beginning of this, when I wrote this down, I didn't know before the fact what the value of the derivative at 1 should be. But I know that if I differentiate the function anywhere except for that gluing point, I can just differentiate like we usually do and not worry about.
for every piecewise that we deal with? Or
Generally speaking, yeah, you can differentiate each of the piecewise each piece of the piecewise function just by usual power rule stuff. But the one place where you have to be careful is where you glue it together. So there, I don't know what's going to happen at the gluing point. I mean, I might be able to lump in one or the other of the cases. I'm just kind of hedging my bets and not throwing either until here, where I decide, aha, it's got to be a half. So in view of that, of course, retrospect of this calculation here, I could go back up and I could include the 1. This formula would get me a half. You probably can include the, I mean, I'm just
confused because you said that, but then
I probably could throw in the case up there too, but just worries me. Yeah.
Where'd the B go in F to F prime?
B is a constant, so it differentiates to 0. But that is a very good question. So I differentiate this expression to get that one. Yes, sir.
Are you always going from left to right to 1? Like when you go from x equals to 1, are you always going to 1? Or is that 1 switch sometimes?
You mean where does this go?
That, yeah, the one under the limit.
Oh, that.
Yeah, is it always 1?
No, doesn't always have to be 1. If I had a different example, like this one, say x squared, x less than or equal to minus 2,
Okay.
and then ax plus b for x greater than or equal to minus 2, then you would be looking at limits going to 2 from the right or left
Okay.
to pick out the a and the b. Yep.
So like if we were given a question in, for our test or something like that, what are we actually trying to find for this? Like if
You're trying to find a and b?
Oh, okay. Oh, okay.
Yeah.
And it's like for continuity.
Yeah, you want to find a and b, which makes the piecewise defined function everywhere continuous and everywhere differentiable.
Okay.
So that was the preamble of the problem in the homework. Something like that. Other questions? Are you guys excited about the test?
Yeah.
I mean, you've been working hard on this material. Finally, you get a chance to show you know what you know.
Yeah.
It's exciting.
Yeah, wait, I have a question. There was one question on
I know.
the homework that looked like x minus 1 or something. Can you work with that?
I think I'm going to need a slightly more specific characterization of the problem, yeah.
All right, I got it. It's, check it out, the limit, I don't have the number here. Well, there is one, I just don't have it. Limit h equals 0, parenthesis 1 plus h, n parenthesis to the 6th power minus 1, all over
Oh,
h.
yeah, I don't know, was that number just on the, homework 4?
It was on homework before, I think, yeah.
Oh, I think I know which one you guys are talking about, the inverse problem.
We didn't have one of those on the test. Did someone explain me how?
There is no more sure way to put a question on the test than to ask me that question.
Huh?
Could it only be on the test?
Are you talking about number 6?
I think it's either, yeah, number.
Show me how to solve it, and then I don't care if it's on the test or not.
Let's see here. So this is the backwards limit problem. Basically, the idea is this. I'll show you an example. Suppose you want to calculate the limit as h goes to 0 of goodness gracious, how about 2 plus h quantity to the 4th power minus 16 divided by h. I mean, I could make it stupider. Let's get nuts. 10th power. I don't know, what is that, 1024? Is 2 to the 10th 1024? Or is it 1012? No, it's 1012. No, wait, no? 1024, okay, I should stick with it. It's kilobyte, right? That's at K, 2 to the 10th. Now, how would you, I mean, obviously, you don't actually want to calculate the limit, right? Because you'd rather not calculate the 10th power of that foiled out. It would take a while, right? I certainly don't want to grade it. So what's the meaning of a question like this? What is it asking you to really do? It's asking you kind of a somewhat circuitous way. First of all, you have to realize, well, this is really the limit as h goes to 0 of 2 plus h to the 10th minus 2 to the 10th divided by h, right? So if you look at this, what you really have is you have f of 2 plus h minus f of 2 divided by h, the limit as h goes to 0, right? Which is what? That's f prime of 2, right? Where f is what? What is f of x equal to here?
2.
No.
Oh.
Say again? I think somebody said it. X to the 10th, right? This is, see, if you take x to the 10th, then you replace x with 2 plus h. It's 2 plus h to the 10th. If you take 2 to the 10th, it's 1024. So you can recognize that this limit is actually the difference quotient for that function at x equals to 2 in disguise, right? But I know how to calculate f prime of x, right? Power rule. So it's 10x to the 9th. So I don't actually have to calculate the limit. I find a workaround. I do 10 times 2 to the 9th. And there you go. That's the value of the limit.
Yeah.
Yep. It's 5,120. But yeah, you could leave it in that form. I mean, I'd be pretty happy if you got to that point. To me, that shows you understand the problem. The arithmetic is somewhat immaterial here.
So instead of doing that, could I also use the turnaround then?
Not really.
Like in the quotient rule?
No. But this is not a derivative. This is a limit as h goes to 0.
But, I mean,
And it's indeterminate. It's 0 over 0. The only tools we have to deal with this limit directly is algebra. You may have been taught L'Hopital's rule in high school. That doesn't even exist for us in this course, I don't think. Or the hospital rule. I don't know. There you go. So, I'm not French, I don't really know. But the point is to recognize the given limit is in fact a difference quotient, so you know how to, you find the corresponding derivative, plug in the point. The problem you guys are talking about in the homework number 3, I talked about the other class, we realized it was in fact f of x equals to x cubed, and the difference quotient was f prime of 1. That was the problem I think you guys are talking about. I could be wrong. Here, again, same idea. Limit h goes to 0. 1 plus h cubed minus 1 over h. Basically, the point is to recognize that that's f prime of 1 with f of x equal to x cubed. So I know f prime of x is what? 3x squared. So this is 3 times 1 squared, which is 3. Can you calculate all limits this way? No. Certainly you cannot. So, but it's good for these particular problems in your homework. Yep.
Okay, so basically you take something plus h and the power, you take x to the third, and you always do that. And then just add the derivative of that.
If you can recognize the given quotient as the difference quotient, as f of a plus h minus f of a divided by h, as h goes to 0, then you can see it's the derivative of that function at that point. Sorry, I can't. I mean, that probably means what you said,
Yeah.
but number 4 from homework 4? It would be my pleasure. Let's see here. Ah, yes, this one is an example of where not to use the quotient rule. See, because now you guys know the quotient rule, so you're tempted to use quotient rule here, but really, there's an easier way. 6x cubed plus 5x squared plus 6x minus 6, all divided by x, and we're supposed to calculate f prime of x. Calculate the derivative. Number 4 of homework for you. Okay, so all I do, my starting move is algebra. So f of x is equal to what? It's equal to 6x squared plus 5x, yeah, plus 6 minus 6x to the minus 1, actually. Or 6 over x, which I wrote as 6x. And then I just do the power rule and linearity on each term, just power rule term by term. So f prime of x is 12x plus 5. 6 differentiates to 0. And then I get minus 6 times minus 1, x to the minus 1, which is minus 2. You get a plus there, right? So f prime of x is 12x plus 5 plus 6, x to the minus 2. Of course, we could rewrite x to the minus 2 as 1 over x squared if we wanted to. Let me contrast this with a similar looking but vastly different problem. I know these backwards limits problems are kind of weird, aren't they? Yeah, he's trying to get you to think, trying to get you to think different as to hopefully understand the idea. The real point of those questions is to try to make it sink in what the difference quotient discussion was, how it links together with what we're doing now with power rule. Because some of you guys hear me talk about, and hear whoever's teaching the course talk about definitions of derivatives, and it just kind of just like goes straight past you. But you can't solve the backwards limit problem unless you understand the definition derivative. So it's nice. It's actually a computational problem which tests whether or not you understand the definition without me just saying, state the definition of the derivative, which is kind of a boring question to ask. Yeah.
Is there practice on backwards limits in the textbook?
Yeah, and I think it should be the problems close to, whatever. Let me see here. What we say? It was number 6 in homework 4, right? The one we were just looking at. That is from. Let's see. I mean, there may or may not be, but if you look at the actual ebook, there probably should be some problems close to section 3.1. 3.1, number 37 is the problem I'm getting. Somebody have their book handy? I can tell you real quick if somebody has their book. Curses, mine's down in my office. I will try to, I have to go back down to my office in about an hour. When I do that, I'll try to get the book and look at it and send you an email about related problems. But, what was I doing? Oh, I was going to show you a related but different example. G of x equals to x over 6x cubed plus 5x squared plus 6x minus 6. this is ever so very different than the example I just did. I can't do algebra to simplify this quotient. The sum is in the denominator. There's no nice way to break this up. You just have to face the music here. You have to use the quotient rule. There's no other way around it. So g prime of x is what? So I do the derivative of the top, dx dx, times the bottom. Minus the top times the derivative of the bottom, which is what? Well, I'll write it symbolically here to start with ddx of the bottom, the denominator function, 6x cubed plus 5x squared plus 6x minus 6, all divided by the denominator squared. And so you do the derivatives. What do you got? 6x cubed plus 5x squared plus 6x minus 6 minus x times 18x squared plus 10x plus 6, all divided by the denominator squared. It's not so important that you write down everything I'm saying here. The important thing is that you see the idea of what I'm saying. So if I gave you a simpler example, you could actually work it out, right? I personally don't really want to grade this. You know, if I was going to ask this question, I would rather ask it in the form, something like, you know, that would accomplish the same purpose. Yeah. Yeah, there was a question?
Yeah. So it was f prime g prime f g, right?
Okay, so if this is, let's say, a over b,
Yeah.
then a over b prime is equal to a prime b minus a b prime divided by b squared. So
Where did
I stated the rule before in terms of f and g, which is probably bad for the purposes of this particular example because we use g in a different sense.
where is a prime there then?
A prime is 1. It's dx dx, you know. So it's kind of, it's hard to, it's easy to miss. Yes, sir. Oh, a quotient problem from 4. Which one do you think you're looking for?
Number 12.
Oh, number 12. I think 12 is a product rule.
Yeah.
But you want to do product rule? Okay. That I can do. Can I, well, I'm going to erase this stuff over here before somebody else asks me a question about it. Okay, so we have f of t 1 plus the square root of t times 2t squared minus 7. And we're supposed to calculate the derivative of this thing. So we do the product rule. Product rule says I take the derivative of the first function in the product, and then I multiply that times the second function, undifferentiated, just left plain, and then plus the first function, not differentiated, just left alone, multiplied by the derivative of the second function. In the AB notation I was just using, it's like AB prime is A prime B plus AB prime. That's product rule. So I have to differentiate those two terms, right? Oh, which one I write first? Yeah, you may have been taught to do this first and that second. Sorry you were taught wrong. It doesn't matter. It commutes. So.
But for the quotient rule, it has to be enough.
Yeah, quotient rule matters because, and that's, by the way, the reason I write it in the order I do, because if you look at the quotient rule, it's the same pattern but with a minus if you use my rule. See? Anyway, so this, what's the derivative? The derivative of 1 is 0. Derivative of the square root of t is 1 over 2 times the square root of t, right? We worked that out. I told you should remember it. You may or may not remember it. Of course, you can work it back out from the power rule. I'll do it in just a second again. Yeah. Derivative of 2t squared is 4t, and the 7 differentiates to 0. And so if I say differentiate, do not simplify, we're done. So that's the derivative. Now, the square root of thing, ddt is the square root of t. Okay, so what happened there? This is ddt of t to the 1/2, right? Which is 1/2 t to the 1/2 minus 1, which is minus 1/2. Which, of course, is 1 over 2 times the square root of t, and that's why I wrote that there. That's just something I remember from here on out. Other questions? Go ahead. Mm-hmm. Ah, yes. Okay. So this is a kind of half symbolic question. It's kind of it forces us to work kind of symbolically here. Number 15, we're given that g of x is equal to x squared times f of x, where what? What else do we know? F of 2 is equal to 3, and f prime of 2 is equal to minus 1. We're supposed to calculate, or evaluate if you like, g prime of 2. That's the problem. And really, problem 14 is almost the same kind of problem, right? If you understand how to do 15, maybe we can understand how to do 14 too. So when I differentiate g, first of all, we don't worry about 2 directly. We try to figure out what's the rule for x to start with. So I try to calculate what's g prime of x. Right. Some of you know, so you're telling me. But let me just emphasize for those who don't. We're differentiating a product. It's x squared times f of x, right? It's a product of 2 functions, so I have to use the product rule. Now, product rule tells me what those folks were just saying, which is 2x times f of x plus x squared times f prime of x. Because the derivative of x squared is 2x, and the derivative of f is, well, it's f prime of x. That's all I can do. I don't have a formula for it. I have to leave it symbolic. See that? So then what? Then I just plug in what I'm given. G prime of 2 is 2 times f of 2 plus 2 squared times f prime of 2. But I have all those things, right? I was given f of 2 is 3, f prime of 2 is minus 1. So I just have to plug them in. So I've got 4 times 3 plus 4 times minus 1. So I get 8. Does that make sense? Or? Other questions? All right, well, I'll let you guys go. I'll see you Thursday, bright and early. Yep. How many questions? Enough? Probably similar to the old test. Yeah. The one that's supposed to be on the website?
Is it just going to be like written
Yeah, I give you white space, you write in the white space. I have the problem, and there's some space to work it, yeah.